Hello and welcome to everybody. First, I'll begin with paying my respects to the First Nation custodians of country throughout New South Wales, in particular the Gadigal people of the Eora Nation, the traditional owners of the land on which the University of Sydney is built. I pay my respect to their elders, past, present and emerging. So good morning and good evening. I'm Greg Watkins. I welcome you all to our Biomedical Engineering Seminar Series. And our speaker today is Associate Professor Anne Vanhoestenberghe from the University College London, the Institute of Orthopaedics and Musculoskeletal Sciences. Her talk today is on active implant technology for electrical stimulation and neuromodulation. So Anne is an associate professor at the University College of London, UK, holds a range of positions in the fields of rehabilitation engineering, active implants and surgical instruments. She's a visiting academic at King's College London and the Free University of Brussels in Belgium. She's worked for 20 years in the field of active implantable medical devices and electrical stimulation to improve the quality of life of people living with chronic conditions. And publishes on engineering education. She regularly participates in equality, diversity and inclusion panels and is also a STEM ambassador working with children from the age of 10 onwards. During the talk, could I ask everyone to keep their mics muted and cameras off until we reach the Q&A part. However, Anne has said she'd welcome questions during the talk, so please feel free if you have something to either put it in the chat box or at an appropriate time call out. She, like all of us, is enjoying the experience of talking to computer screens and wondering who's on the other side. So with that, I'll hand over to Anne to introduce her talk and tell us about her work. And thank you very much.
Thank you very much, Greg, and thank you all for the opportunity to present my work today. And I would say to start, it's 11 p.m. for me here, so if I sound a bit ropey to start with, I'll probably quite quickly get into my stream, but right now I'm thinking it's the time when I would normally start switching off. So if you have any questions, I'm going to try to monitor the chat as I present. If I don't seem to see your question on the chat, feel free to just unmute and interrupt me. As Greg was just saying, it is a little bit weird sometimes when you're talking in front of a screen and you think, have I gone mad and am I really talking just to myself or are people listening? So if you can hear me, just let me know you're still there every now and again. In terms of the talk, I wanted to talk to you about sort of technology for electrical stimulation and neuromodulation, and I've broken down the talk in 5 subtopics. I'll start with a sort of introduction, telling you a little bit about myself, but I want you to make a decision as to which of the topics I'm going to talk about. I will impose on you the talk about bladder control after spinal cord injury because it's the dearest to my heart. It is the one that I see the most important because it's the least covered. It is the least appealing. No one wants to talk about bladder control, so I will talk about it. And I'll try to really explain why I think this is so important. But I have other topics, and 2 of them are really technology developments. 2 are discussions of tests and studies that we're doing with people. So I'm going to ask you in a moment to vote. Anchoring is a topic of how we can fix electrical devices that are destined for stimulation or recording inside the body without causing the body to reject them. And this will include animal model work, but no work on patients. Polymer encapsulation is purely technology. So this is the development, this is what I do most, but maybe not always the easiest to get across because it's a bit dry. So this is going to look at the corrosion prevention at a IC level, so on silicon ASICs. ES, electrical stimulation and blood flow. This is a simple study we did going back to people. So we work with people with spinal cord injuries, we work with clinicians, and they were expressing a problem that, again, according to them and to a lot of people who suffer from a spinal cord injury, is poorly understood. And so we started a series of studies trying to answer a question for them. And EMG-driven artificial larynx control, this is a control study that we're doing. It's got a lot of interesting prospects and applications, and it's also interesting in the results that we're finding, but it is a control application. It's not an electrical stimulation application. So I'd like you to put in the chat A for anchoring, P for polymer encapsulation, ES for electrical stimulation, and EMG-driven artificial, EMG for EMG-driven artificial control. Rank them in order of your preference. Bladder will start anyway, and then as I start through bladder, I'll ask you, I'll check the chat and I'll see how many votes we have for each of these four. And this is what will decide the second part of the presentation in a way. So you can start. I'm hoping you'll get at least one vote. Otherwise, I stop after bladder. Before I yes, I'm getting responses. Brilliant. Okay, so we're seeing polymer encapsulation coming on top here, and just briefly telling you about who the controller in the way for me. I can't see what I'm doing. So as I've been introduced very briefly, my main field is the protection of electronics operating inside the body, which is going to be the P vote, if anybody votes for that. In terms of my career, very briefly, I joined the implanted devices group after my university degree, and for about 10 years, I worked in the group led by Nick Donaldson. I wrote the heritage of Brindley and Peter Donaldson neuroprosthetic units, because they are to me, the pioneers who founded a lot of the work we've been working on. In 2008, I had the great pleasure of spending a few months with Greg Swenning at the Australian Vision Prosthesis Group, which was really formative. Again, I learned a lot from being there. Although the time was short, it was a fantastic atmosphere. It showed me a lot more about collaborative development and truly multidisciplinary teams. The work that was done was focused on, there was one mission and so many different inputs. And that really inspired me to reproduce some of what I'd learned there in terms of the team I was trying to create. I did also spend a few months at IMTech with Martin Schuttler and Thomas Stieglitz. And again, I was there, they were much more focused on technology there. The focus on people was absent. And the ability that it gave me to look deep into the technology development was again very formative. So I was equipped with these thoughts from the 2 short periods I spent in 2 other groups other than Nick. I returned to UCL and I founded or co-founded the Aspire Center for Rehabilitation Engineering and Assistive Technology, which sort of shortens in the word CREATE. Aspire is the charity that funds us, so our group is usually called Aspire Create. Worked quite well, I like the words as well. So where is CREATE related? We are sited on the site of the Royal National Orthopaedic Hospital. To us, that was really important to be on the site of a hospital, because our mission is to lead translational research. We are focused on improving the quality of life of people living with spinal cord injury, but as you will see, a lot of our work has applications beyond the field of spinal cord injury. It is truly a joint academic and clinical venture. So we are a group of academics sited within a hospital campus, and we work regularly and participate in meetings with the clinicians. It currently has 6 academic staffs, 8 postdocs, 8 PhD students, and used to have a lot of clinicians affiliated until the COVID pandemic hit us, and all of our clinicians are now working full-time managing the workload that the pandemic has caused. So the last bit here is gone. We have a website which is never kept up to date, like every group's website, but we do our best. You can see some of the work that my colleagues are doing if you go to ucl.ac.uk/aspirecreate. And I've just really summarized it briefly to give you a little bit more of a desire to see what we're doing. So I work mainly so these are 5 cross-cutting themes. Every theme will work with others. So I work mainly in the theme on electrophysiological interactions, where we study neuromodulation, electrical stimulation, transmagnetic stimulation, and we do biosignal processing. We have a group who works on human-machine interactions, and they kind of range from BCI to haptics. I also work with them on adaptive shared control systems. These control systems will then be applied to robotics, where you can see here a study on an exoskeleton. We have smart wheelchairs, again, embedding a lot of controls to do shared control. We work with tricycles, and we have a special theme that studies surgical robots interactions. We have a nascent group working now on the development of wearable sensors and stimulators. And then my main interest, which is active implantable devices, which includes instrumented orthopedic implants, as well as electrical stimulators. And we work both in the implanted devices group, of which I'm still a member, We work on the development of the technology, whilst at Create, we work on the development of the applications. The Implanted Devices Group is directed by Professor Nick Donaldson, who founded the group in the 1990s at UCL, after working for about 25 years in the Medical Research Council's Neural Prosthesis Unit. It's usually shortened as MRC-NPU, which was led by Giles Brindley, and Peter Donaldson was the lead engineers. And they pioneered work such as this visual prosthesis here. So this is Brindley here working with a patient describing the visual sensation that they are experiencing as they are being stimulated. This, just to give you an idea of the size of the implants, you can see the X-ray here, the number of single units that were implanted to try to achieve visual stimulation. This group is considered by me as having established non-hermetic packaging for medical implants. They did not invent it, but they did things like this. This implant, here we can see the external part, here you can see the internal part, and they combined a hermetic package for some of the electronics with non-hermetic protection using using silicone for protection of some of the electronics. They did not invent it, but they made it work, and it's worked well enough that this is Julie Hill. She was one of the patients that was implanted with that system, and she was then the subject of a BBC documentary and later a movie. These are not actors, these are the real people, Julie and her husband, and this is Tim Perkins, who is one of my colleagues at the Implanted Devices Group. The focus of the IDG is much more on implant technology. So this is a picture of our lab before the lockdown. I don't know what it looks like these days, but a year ago, that's what it looked like. We had several water baths with a complex test system. And I'll tell you a little bit more about that because I'm seeing that the polymer encapsulation is coming on top, closely followed by the others. So we'll certainly talk about polymer encapsulation, and then we'll see. So this is it, enough for the introduction now. As I said, it all started for me with bladder control after spinal cord injury. Believe it or not, this is what attracted me to come to London. That was my project when I thought, oh, I'm going to go and do ASIC design for bladder control after spinal cord injury. I won't talk to you about ASIC design, but I'll just briefly introduce the complexity of bladder control and the reason why it interested me. In function, the bladder should, as we all know, hold fluid in a controlled manner. Its function is also, and we sometimes forget that, to void precisely and at a convenient time. Anatomically, the bladder is very simple. It's a simple bag with a sphincter that holds it closed. In terms of control, it is way more complicated. The bladder has 3 different centers of control, and they interact with one another in a series of reflexes. This is a relatively simple representation. The consequence of this complexity and the fine balance between the different inhibitory and excitatory reflexes that control our bladder, both in terms of controlling continence and controlling voiding, mean that after spinal cord injury, it all goes wrong and it's dramatic. We see incontinence, we see bladders that neither fill at the proper rate nor empty at the right time. And I was attracted by this because I was presented with a challenge, which was, could you rewire this? I know 20 years later that we're not rewiring anything. What we're trying to do is to think outside the box and provide alternative methods to return function, that is to return the storage and the voiding functions for people who have lost it as a consequence of a spinal cord injury. This is not new. The first part of the bladder assistance is assisting the voiding. So the voiding function needs to be supported. And this was done very well by Giles Brindley in his days using a sacral anterior root stimulator implant. It's a simple system that stimulates the anterior roots that innervate the detrusor. And on demand, you can provoke a contraction of the detrusor muscle, which leads to voiding. But it has 2 minor issues. The first one is that it relies on an afferent rhizotomy for continence. In other words, by cutting the afferent nerves, it prevents reflexes that would otherwise cause incontinence at small volume. So the bladder isn't ready to void, it shouldn't be voiding, the volume is very small, but there are afferent reflexes and the bladder will void. To avoid this, the surgeons used to cut the nerve roots. Now, this is no longer a procedure that surgeons are comfortable with, and patients are also often uncertain about the idea of cutting more of the cord that has already been damaged. A second issue is that it is not suitable for users with intact sensory pathways because the stimulation can, in some cases, be painful. So we're looking for alternative sites to assist the voiding in a way that might not need the rhizotomy or that might not cause quite so much pain. And which sites that are being tested, whether they are peripheral nerve or stimulation directly of the detrusor, face the same challenge, which is that we need to have access to the site and have a long-term fixation of the electrodes. Where Brindley placed the book electrode that are used in the SARS inside the spinal canal, the book electrodes are protected and they're a very easily accessible site. Anywhere else, and you run the risks of around the peripheral nerves, they're very fragile and there is a risk that they will get damaged. And at the detrusor, there's another problem, which is that the device can detach itself either outwards and get lost inside the body or inwards through the detrusor wall and find itself inside the bladder and then cause a host of infections and other issues, secondary issues. The other aspect of, so we talked about assisting voiding. We also need to talk about continence and preventing voiding. And this is work I do with my colleague, Dr. Doherty, who was a PhD student with me, Lindsay Duffel, Sarah Knight from the Royal National Orthopaedic Hospital. We work a lot on neuromodulation or blocking. There is a vast literature on animal models, but there is very little that has translated into humans. And this is quite typical of this field. Spinal cord injuries are complex, and it is really difficult to conduct study on people who suffer from a spinal cord injury because the causes of the injury may be different and the consequences are usually different as well. An animal model enables you to control and have an exactly reproducible context. In the context of human work, we find that a lot of what has been demonstrated as working on cats does not translate to humans. So we run our own study, and this is the first of the study that I'm going to present today. It is published. I haven't quite got the space here to put the whole title, but I'm obviously happy to share all of the papers that I'm going to be mentioning today. So what we tested was, we tested 4 different sites in the following process. So the participants took part in 4 sessions, 1 per site. They would stop their medication for 5 days prior to have no longer any effects of the medication. We do a baseline cystometry, which is sort of measuring the bladder response. We look for the presence of neurogenic detrusor overactivity. In other words, we look for the bladder to empty when it's not full, which is what we're trying to prevent in this context. And that's one of our inclusion criteria. If the participant presents neurogenic detrusor overactivity, we will test what stimulation parameters can be used to prevent the contraction, and then we do 2 cystometry studies with neuromodulation. The 4 sites tested are the dorsal penile nerve or dorsal genital nerve, the tibial nerve. We also did spinal cord stimulation and spinal root stimulation. We recruited a number of participants. Only 7 completed the study. That is, they were able to complete the 4 sessions within the time allocated in our protocol. And on all 7 of them, what we observed is that the dorsal genital nerve stimulation was able to significantly increase the end of field volume. So that is the volume before contraction. And although it may seem like 100 milliliters is very little, for a person with a spinal cord injury, it may be the difference between an incontinence episode at a time which is inconvenient, or having time to reach a bathroom where they may be able to empty their bladder in a socially acceptable way. So we're not trying here to restore full bladder volume. We're trying to restore enough control and enough continence that a person can have a socially acceptable and socially convenient voiding strategy. We also found in our study that no patient had a negative effect. That is, all the stimulation showed either no changes or an improvement, which is really important because spinal cord injuries are so varied. Sometimes studies show that you have positive effect in some participants and a negative effect in another participant, putting into question the applicability of the strategy that is being developed. In doing this study, one of the challenges was that during the study, we detect the bladder contraction with our own embedded sensors. This obviously cannot be done for a person using the strategy on a day-to-day basis. So whilst we show that the neuromodulation would be very suitable for some participants and might have benefits for a lot of participants, we needed to find a way for the people to know when to turn on the stimulation. Now, here's something really interesting. If you work with a bunch of engineers, there are things that we don't know. Mainly, we don't know what it's like to have a spinal cord injury. When you work with people who have a spinal cord injury and for people who work with a spinal cord injury, so Sarah Knight runs the urology services for the whole of the Spinal Cord Injury Research Center in Stanmore. So she sees hundreds of patients. And what she was able to tell us, as well as all patient advocates, was that yes, a lot of work has been tried on detecting the bladder activity using EMG, intravesical pressure, and they all have severe issues that make them, to date, highly unsuitable and unlikely to be applicable for years to come. Sarah and others told us, but most people have sensations. And this is really surprising to us. So we ran an audit of data from 313 patients that come to the services, to Sarah's services. And what was found was that in the incomplete population, so these are patients who with the vast majority are wheelchair users, but they haven't got a complete section of the spinal cord. And as a consequence, they are expected to have some remaining pathways. What surprised us was that nearly 92% of them had some form of sensation of bladder fullness. They could tell when the bladder, no, sorry, not bladder fullness, bladder contraction. They could tell when the bladder was starting to be active, even when it was relatively unfilled. So it could have a small volume and they could tell you, oh, I can sense that it's starting to contract. Even more interesting, in the group of complete patients, these are patients whose spinal cord has been completely transected. There are no longer any direct pathway. People express the ability of detecting when their bladder was contracting for about 45% of all participants. It's really important to say that the sensation isn't the same as the sensation you and I experience. They have aberrant reflexes. The bladder has reconnected to other parts of the lower body, and so they may feel it as a sensation of maybe leg movement or leg contractions, or sensations of heat in areas of the body, different aberrant sensations which they have learned to detect and to interpret as being an indication of bladder activity. That meant that in the total of the over 300 participants we tested, over 75% of the spinal cord injury population could use a device to block activity that they would turn on themselves. They don't need to be told when their bladder is about to contract, they know it. This was remarkable. It sounds obvious, the data seems so obvious, and yet no one had yet done it by simply saying, could you turn it on? So we sent several people at home with our devices, and they're trying it at the moment with their own sensations. We then proceeded to work for the 25% of the population, most of whom are complete spinal cord injury patients, on how to detect bladder contractions for these people. And we've been working on trying to detect deformation. So this is not based on volume, because we know that the bladder may contract at a very low volume, but we're trying to detect movements of the bladder muscle. And that brought us back to the same issue as previously mentioned, which was this issue of how to anchor a stimulator or a sensor to the bladder wall. And I told you earlier that I was influenced by the work by Giles Brindley, and having worked directly with Nick Donaldson, I had the great pleasure of meeting Giles Brindley several times. And the second meeting, I'm meeting a person who's kind of my scientific hero, and he immediately started talking to me about bladder control and all of the tests he did, included tests he did on himself and the sensations that these different tests did for him. I know Greg Swinning met him, so I expect Greg's laughing now because he knows what it's like to be at a table with Brindley and he kind of goes on talking to you about something. Bear in mind, at the time when I met him, I was very impressed. And he told me that one of the biggest problems that they'd experienced when they tried to work with attaching devices to the bladder was that the body was able to absorb and proceed with expelling the devices they were trying to place. So they were attaching them to the outside of the bladder, and somehow later on they would find the device inside the bladder, causing lots of infections and other reactions because it's way too big and it can't be expelled through the urethra. He then brilliantly then sent me this paper by a colleague of his who had in 1994 tried to find the best way to attach something to the bladder. And this is what he wrote. Electrodes eroded through the bladder wall into the lumen or lost contact with the bladder. When they lose contact with the bladder wall, this is that they go elsewhere in the body. This is written in such a way that it tells you, we tried different positions. Those that were in this first position, the site is useless. Second set of position, this site also cannot be made useful. Last position, and I'm skipping for you the exact positioning, it's not relevant here, simply to say that the most promising site still involves some risk of erosion into the bladder. And that was what concluded the efforts of Brindley in the 1990s to try to attach a device to the bladder. And between 1990s and now, no one has succeeded in making this work. There's been several attempts, and every now and again I will see somebody present something and then they will say, but we don't really know why, it's not really staying stuck. And I'll refer them back to the work that was done back 20 years ago. So here we go. I've done the presentation of one or two studies we've done on bladder work. We now have a choice of different topics, and I've seen in the votes that I think polymer encapsulation, electrical stimulation, polymer encapsulation. So we'll do polymer encapsulation first, then electrical stimulation and blood flow, and then we'll go to the EMG. So the polymer encapsulation, if this works, here we go. So silicone rubber encapsulation. By all means, do ask questions. If you had any questions about the bladder, do interrupt me before I move on to the next topic. Otherwise, I'll talk to you now about silicone rubber encapsulation. The first point I will make is it works. It is used currently in a device that is CE approved, that has been implanted in hundreds, if not thousands of patients, and they have benefited for decades of really good operations, very high reliability. So it works, and it doesn't just work on 1 or 2 people for about 10 days or whatever acute studies you can see. Silicone rubber is not a barrier to water. If you look at this paper from the 1970s, 1977, one of the most reproduced image in our field, you can see that silicone rubber, a thin layer, will be saturated with water vapor in minutes to hours, depending on the thickness. In other words, the way it works is not by preventing water to penetrate, but by preventing the formation of liquid water in contact with the conductors. If you look at this paper, the dotted area here represents the silicone rubber. And what it shows you is that if silicone rubber covers every surfaces, in particular every conductive surface, then no liquid water can form. And if there is no liquid water, there cannot be conduction between 2 conductors, and there cannot be corrosion. And this is, in a nutshell, the principle by which silicone rubber encapsulation works. We know that it will work as long as the surfaces on which it is deposited offer a very good adhesion, and as long as these surfaces themselves are not permeable to water vapor. The problem then is, well, okay, for a metal, it works. We know that if you prevent formation of liquid water over a metal, that's fine. But when you start working with ICs, we know that the surfaces of the ICs are not finished with metals, but with passivation layers. And we did a study, which I will present, oh, that little image, which I'll present to you today. Again, this is published, and this is in the process of being published. Sorry, it's not out yet. And I will share with you details. It's a survey of silicone encapsulation on thin film silicon oxide, silicon oxynitride, and silicon carbide. And it's a long-term aging study. And we compared the effects of these different passivation layers on top of a simple interdigitated structure, so a set of 2 electrodes, we have demonstrated that if you vary the different parameters of this set of electrodes, ignore the pink line here, this is a shield line that's used for other reasons. But if you vary the parameters, you can vary the depth of the sensor. So this acts as a corrosion sensor, and we can vary precisely to sense any changes in this area right between the silicone rubber and the passivation layer, here presented as a silicon oxide layer. So we create our sensors to be very sensitive to about the 1000 nanometer region. This is the picture I showed you earlier. This is our test bench, and in a simplified version, what you can see is that every single one of these hole here holds one sample in its own water bath. It's kept at a constant temperature. Each of them have their own water content, so there's no contamination from one to the other. And we can apply a bias to all the sensors. So we have 96 samples per bath, and we have a series of baths at different temperatures. So these two show you the 66, 67 degrees test. They are regularly tested with electrical impedance spectroscopy using a Solatron system. The study that I'm going to report on today compared 5 different batches. What you're going to see here is that we have 3 different types of passivation: silicon oxynitride, silicon oxide, or silicon oxynitride with a silicon carbide, and 2 different silicon rubber. There was, as you can tell by the names of the batches, there was a batch A, but there was a fabrication failure, so we have no results to report on batch A. The study ran for a couple of years, a little bit more than a couple of years, so we have data up to 694 days. And unfortunately, due to manufacturing issues, some of our samples are relatively small, but even in these small samples, we saw very few failures. ENTC stands for interconnection failure. So that's, again, failures that are due to the manufacturing process. IDC failures, the failures that we were looking for, these issues where the IDC, the interdigitated the interdigitated comb, shows us that there is a failure of the silicon rubber, only occurred in one batch, batch C. In other words, a combination of a passivation layer of silicon oxynitride with silicon carbide or without silicon carbide, protected by either of 2 types of silicon rubber, gives no corrosion, no detectable corrosion with the most sensitive picometer measurements we could do for a period of 2 years, under bias in heated water, so in an immersed, heated environment. And this is just to show you briefly the results that we observed. That shows you that what I mean by failures is not a gross failure. There is no, you still can't see the corrosion, but all sensors are extremely sensitive. And we started detecting, after a period of time, a change in the impedance, in the magnitude of the impedance spectrum, and a change in the phase of the impedance spectrum. So you need extremely sensitive equipment to detect this. This is not a functional failure. But after 2 years, the PhD student Callum just complained that his PhD was failing because nothing was failing and he had nothing to write about. All he had for 2 years of hard work was this little change. So he spent a long time analyzing not very many data. But this was very, very good for us, of course. We care about having as long a lifetime as we can. He cared about finishing his PhD in 3 years and getting a thesis out of it. But he's done fantastic work. So just very briefly, what he observed in batch C, the batch that failed, the only one where we can try to understand what causes failure, probably the failure mechanism in this batch would be similar to the failure mechanism in the other, but they may just be much slower. And what he observed was a hydration effect. So you can barely see it on these 2 images, but as you dig through the different layers, so the top of the IC is here, and as you dig through, what you're going to observe at about 600 to 700 nanometer is a change in the composition that indicates that the top layer had become hydrated over time. So what we think happened is that as the silicon rubber we know is not a barrier to water, water vapor penetrated through it. No liquid water formed over the passivation, but the silicon oxide itself very slowly absorbed a little bit of the the water vapor that had penetrated through the silicone rubber, forming a hydrated layer. And this was sufficient to cause changes in impedance and in phase that were progressively observed as these changes. This is one of the batch C samples showing you the effect of drying it. So as it was dried after aging, the phase recovered slightly. So this is all I'll say today about electrical stimulation. Sorry, that's the next topic, about polymer encapsulation. My main message here is really it works. It works even for, if we go back, even for ICs coated with silicone rubber with a simple passivation layer as protection, provided your passivation layer does not become hydrated. And this is further work that is ongoing on that. So I'll just share this image again for the silicone we tested and the different passivation layers we used for anybody who's interested in learning more about that. I think the next topic is going to be, what did we have? ES and blood flow, a lot of electrical stimulation, larynx control. Yeah, we'll go to ES and blood flow. Oops, too fast. So as I said, this one is a study on healthy volunteers. The context of that is our colleagues, the clinicians with whom we work, tell us that the spinal cord injury population suffers a lot from. Oh, I got a question. Sorry, I'm just going to answer this question. For the encapsulation, why water and not saline? We have previously tested the fact that the silicone rubber is completely impermeable to the salt that is contained in the saline. But these tests, some of the tests are actually done in PBS. So after some skepticism from some of our reviewers, I think all of Callum's tests have been done in PBS. So I apologize. I'm used to saying water because we demonstrated previously that a test in water had the same results as a test in saline, but we have been working in saline. We're also looking at actual components of body fluids that do impact the silicone rubber, such as the presence of lipids or reactive oxygen species, and there they do make a difference. So, but apologies, it was PBS for Callum's thesis. He was the first to systematically use PBS. So in electrical stimulation, thank you for the question, by the way. In electrical stimulation, on the topic of electrical stimulation, in spinal cord injury, about 80% of the people who have a spinal cord injury would suffer from at least one pressure ulcer over their lifetime. Pressure ulcer develops because the people tend to sit for long periods of time without moving at all. And so areas of high pressure develops usually under the coccyx and other areas which are where prominent bones are. This means that for the period during which they have to heal, they cannot apply pressure on the area that has suffered from the pressure ulcer. If you are unable to stand and your only means of mobility is being in a wheelchair, being told that you can no longer sit means you no longer go anywhere. And to relieve pressure, especially when the pressure ulcer is in the area of the coccyx, the position that you must adopt is lying on a bed, face down, to relieve the pressure on the back. And healing from a pressure ulcer can take weeks to months. So spinal cord injury people are likely to, at several times in their life, find themselves bedridden for a period of weeks to months, something that they just do not feel until the pressure ulcer has grown to a stage where it actually can be. Some patients report that they could smell it before they could feel anything. So it's a serious impact. It impacts their rehabilitation, it impacts their independence and their quality of life. And just like the bladder, it is something that is little talked about amongst researchers unless they work directly or know directly people who have a spinal cord injury. But it's an extremely high priority for spinal cord injury patients. It is also a high priority for our governments who pay the bills, because the cost of dealing with pressure ulcers represents a high cost in the overall spinal cord injury treatment cost. It represents a high cost in the overall budget as well. So to just put this in perspective, the spinal cord injury population in the UK is very small compared to the population of people who are obese, and there's about a 1-to-10 ratio. But the ratio of, morbidly obese 1-to-10 ratio to spinal cord injury, but the the 1.4 to 2.1 billion a year cost of the pressure sore only, that's about 1/3 of the total budget dedicated to all causes and diseases related to morbid obesity. So small community, very high burden. Electrical stimulation as an adjuvant for pressure ulcer healing in spinal cord injury is already recommended by several associations, but a Cochrane review published in 2020 showed that evidence of effectiveness was limited. There was some, but it was of low quality. And part of the reason that was given was that the mechanisms of action are complex and poorly understood. And so in collaboration with our colleagues, we wanted to do a study to try to better understand the mechanism of action so that an interventions can be developed dedicated to spinal cord injury people. We focused our attention on short pulse electrical stimulation. So this is low frequency electrical stimulation. And this was inspired by several publications by Cramp and his team, who demonstrated about 20 years ago that when electrical stimulation in short pulses at low frequency is used above motor threshold, it does increase blood flow. The question that remained from this series of papers was that if you work above motor threshold, the change that you're seeing in the blood flow could be due to a neuromodulatory effect, but it could also be due to muscle contractions because you're working above motor threshold. It could also be due to localized heating due to the muscle contractions, so a secondary effect of the muscle contractions. We wanted to test the hypothesis of low frequency electrical stimulation below motor threshold. This would then enable us to test whether the effect was purely due to neuromodulation or whether the effect was due to muscle contractions and possibly localized heating. So we recruited 32 volunteers. This is done on healthy volunteers and it's done on the forearms rather than the areas where pressure ulcers mostly develop, because it's a lot easier to recruit volunteers to have a test done on their forearms rather than on their buttocks. So we had 32 volunteers who were randomized in an electrical stimulation group or a placebo group, and the intervention was blinded to the participant. So every participant was set up, every participant was tested with electrical stimulation, and then they were told that we would randomly adjust the amplitude of the stimulation, and we turned on the stimulator for all of them. For some of them, the stimulator was turned on, but with no current going through, which made them then all placebo group. In terms of outcome measures, we looked at the forearm blood flow. We also looked at variations in oxygen saturation in the blood, and specifically we broke it down in oxy and deoxyhemoglobin concentrations. And we also looked at the forearm temperature on both forearms to try to answer the questions of whether or not there was any localized heating effect. So our setup is presented here, where we have electrodes used for stimulation, and we have we used NIRS, near infrared spectroscopy, for the assessment of oxygenation in the blood, so oxy and deoxyhemoglobin. And we had a thermistor on both arms so that we could distinguish whether there was any local temperature change versus a global temperature change. The process included the subject setup and initial measurements where we set up the electrical stimulation. Then everybody had a minute of rest. And then we proceeded with 3 baseline venous occlusion. Venous occlusions are the method used to measure the forearm blood flow. It comes with some inconvenience, as I shall demonstrate very shortly. Then there was a 15-minute baseline during which we recorded the participant did nothing, was simply seated comfortably without moving. And then a 15-minute intervention where the electrical stimulation was turned on, and then the participant was allocated randomly by the stimulator in the electrical stimulation or the placebo group. And then we repeated venous occlusions 5 more times over a 10-minute period to observe any changes in forearm blood flow. Here is what the data looks like for the ES group and the placebo group. This is the total hemoglobin concentration changes over time. And you have indicators here of when the baseline started, the intervention started, and the intervention was terminated and followed by 10 minutes of venous occlusion. And this little corner here, I hope you can see my mouse, by the way, otherwise I'm pointing at things that you can't see, but there is a zoomed in version here over the placebo corner. Thank you. This is what happens when you do a venous occlusion. So the principle by which the venous occlusion measures the forearm blood flow non-invasively is by causing an obstruction, so an interruption of venous blood flow and then a return of venous blood flow, which causes sudden changes in the total hemoglobin concentration. And the slope of these curves enables precise calculation of blood flow. The problem with that is that it completely disables any readings of oxygen concentration other than in response to the occlusion. And it causes movement and discomfort to the participants. So we were not able to repeatedly cause the venous occlusion. So we have data about blood flow before and after the intervention. And this is why this plot is hollow, empty in the middle. We also have data on oxygen saturation throughout the intervention. I present this study despite the fact that we have next to no significant differences, because I think it's really important yeah, time check 10 minutes. Yeah, I'll just finish after this one. It's really important to present this study in as much as with 32 participants, we just didn't have enough. Then the pandemic happened and we just, well, our project is finished and we're trying to raise more funds to try to continue this study. We started seeing what looked like a trend in the electrical stimulation. So we may have detected something. There's one significant difference between electrical stimulation and placebo. What we've also identified is that we need another method to non-invasively measure the forearm blood flow, but we also need a larger cohort, which we were hoping to go for before the lockdown stopped us and finished this project. So I think this really shows you that at least in my experience, working with spinal cord injury patients is extremely difficult. The first study I presented in bladder had only 7 participants. Working with healthy participants enables you to recruit. Usually we can get to 60 participants relatively easily if there isn't a global pandemic closing your lab. But even then, the issues with people is that they're all different and they all behave differently. And when you start seeing something like that, it's extremely exciting. As an engineer, I would expect strictly significant differences everywhere if I made a product and I changed something in the design. But as a scientist who work with people, I get excited when I see the indication that maybe if I had twice as many participants, I might be able to statistically have more confidence as to whether this is a fluke or this is a trend. So I think we have 10 minutes now, so I'm going to try to leave you time for questions rather than discussing another topic, unless we have no questions, and then I can go on with the control study. So over to you.
Okay, and so thank you very much for a very interesting and engaging talk. I'm sure, I know I've learned something. I'm sure that we've all learned something. So thanks very much. So are there any questions that people would either like to call out or to put in the chat box, please? I'll start with one to get things going. And you talked about spinal cord injury patients having some sort of sensory perception that told them that they needed to void their bladder, or their bladder was starting to fill. How reliable was that sensation? Were there lots of false triggers? And if there were false triggers, are there any side effects of the electrical stimulation they then triggered?
No, so there's two really good questions in here. So the first one is, these sensations are relatively reliable. It's an audit, so we haven't monitored these people for longer than the time that they come to see us. So we equip them with ambulatory urodynamics whilst they're in the hospital. They spend about an hour with us, and in that hour there's very little false positive. They know when they're going to have a contraction. Not every contraction leads to an episode of incontinence. So at home they may say, oh, I feel that all the time, and it's not always a contraction. But when they're in the lab and we have urodynamics, we can show them that actually they're quite right. It's just that sometimes their bladder contracts and it's so empty that nothing leaks. There's no leakage. So we find that once they're given this information, they can then refine the detection of their sensation, if you want. Bear in mind, in the complete section, so in this group here of 100 and some participants, it is not a normal sensation. So they have to learn to recognize it, and they do that by watching the pressure profile. So we display the bladder pressure profile to them, and they then learn to say, oh, this is the exact kind of indicator. I'm hesitant in calling it a sensation. It is a sensation, but it may be best to just call it an indicator of bladder activity.
Okay, thanks very much. There's a question from Alistair in the chat box.
Yes, thank you. Hi. So have you found aging a problem, tissue changes in the bladder wall sensation, an issue for bladder control? Definitely yes. So it is well known that as a person with spinal cord injury ages, spinal cord injury is a single point of injury, but with a chronically decreasing quality of life. So it's expresses itself in many different ways, and the bladder wall thickens. That is due to overuse. It may also be due to the drugs that they use. They take anticholinergic or antimuscarinic drugs. So we do find that there are problems. Greg, one of your questions was also about whether the electrical stimulation causes problem. As far as we know, electrical stimulation has no long-term side effects. So there's no degradation due to the electrical stimulation, but there is a general thickening of the bladder wall over time. I see I've got questions from Greg as well. Can the patients with complete spinal cord injury also detect the absence or presence of electrical stimulation? As far as we know, they don't. Brindley is the only person, well, Brindley and Mike Craggs implanted incomplete people and people with other causes of NDOs. I'm going to say NDOs, I can never say, neurogenic detrusor overactivity. And in that paper, they published a paper on about 50 patients. Some of them had sensations, and they did report that the sensation were unpleasant to the point where some stopped using it, using the stimulation. So they can feel the stimulation, and they can feel it's unpleasant if they're incomplete. In complete participants, they can't feel it. I've only ever asked one person whether they could feel it in the way I think you mean, Greg, is that do they get a sense of whether it's activated or not? And one person said all they could tell was when they hear it. They hear the urine coming out. It makes noise. That's when they know they're voiding. So no, they don't feel the stimuli. And another question, with the ILSA study, you tested people without spinal cord injury. Do you have a view as to whether their response to the stimulation would be the same as a person with spinal cord injury? So yes, there's quite a lot of evidence that the neurophysiology below the lesion is intact. The people with a spinal cord injury respond in a very similar manner to the people without a spinal cord injury when you're some distance away from the lesion. So where we do peripheral nerve stimulation in spinal cord injury, we get similar reflexes, similar H responses, similar muscle contractions. The muscles have wasted, so there is a difference in the response that is recorded, but it's no dissimilar to what a wasted muscle in other conditions looks like. When you look at the level of the injury, it's completely different. So it's inappropriate to do a healthy study for something that has to do with a reaction around the level of the injury, but it is fine for something that might be mediated on a peripheral nerve level near the site of the pressure ulcer. Tibial nerve stimulation for bladder control, we did test it. I'm going to try to go back.
I came a bit late.
Yeah, yes, no, it's really interesting. So there's one image that I'm going to show you here. So tibial nerve stimulation showed no significant improvements in the end of field volume, but it did show us something that I haven't showed here is we think it might actually be dangerous because it increased the detrusor, the internal detrusor pressure. So that when the bladder contracts, if the sphincter doesn't relax, then there is a risk that urine goes back up through to the kidneys if the pressure increases. So when you do bladder voiding, I mean, I didn't cover it here, but to do assisted bladder voiding, you must void the bladder in a low pressure mode to prevent reflux into the kidneys, which used to be one of the major causes of complication and secondary complications and death before the introduction of antimuscarinics, which stop aberrant bladder contractions and make the bladder placid. It was this overactivity leading to reflux in the kidneys and kidneys infections and septicemia. So it's a really big issue. So tibial nerve stimulation may be effective at first sight because it does enable the bladder to fill more, but we think it's because it increases the tonus in the sphincter. And that's not desirable because of this risk of then reflux.
So it's better for fecal incontinence?
So it would have some benefits in some types of incontinence. If the incontinence is due to sphincter weakness, it would be really interesting. In the spinal cord injury population, where the incontinence is more due to these aberrant contractions of the detrusor, we think it could be very beneficial for some, but without a constant reviews of the cystometry to see the bladder pressure, we don't think it's advisable. Are there any further known uses for neuromodulation in patients with nerve injuries, spinal or otherwise? Wow, that's a vast question. Yes, there are. I mean, there's obviously all of the deep brain stimulation, which is a form of neuromodulation. There are vagus nerve stimulation and neuromodulation. There's a big push here on obesity. One of the things I didn't show you here, the adaptive electrical stimulation as part of anchoring, which was a study on moderating food intake. This is an animal study, moderating food intake using electrical stimulation. So that's a neuromodulation study on obesity, because obesity is such a huge, I mean, it is a pandemic, it's so big, there's a lot of work on there. So this is adaptive gastric electrical stimulation. I think we are out of time, but yeah, there are a lot of other neuromodulation applications.
Yeah, with apologies to people there. So thanks very much for some great questions, and thanks as well to Professor Vanhoestenberghe for I think a really interesting presentation, engaging presentation. We are coming up at the end of the time, so we'll call it there. It's midnight in the UK. Thanks again, very interesting, very engaging, and thanks also to Kevin and Cecilia who helped with the logistics of arranging the session. Okay, and a few thanks coming up in the box.
Yes.
Okay.
Thanks a lot.
So,
I've put my email on this last slide, but you can contact me. So if you have any questions, want any of the papers that I mentioned, or want more details on some of the topics, I was trying to kind of go quickly through different topics to give you a little flavor. And so, yeah, just let me know. And I wish you a very good day.